Hello everyone. Welcome to part B of the first lecture of Engineering Math 2032, Probability and Statistics, which reminds me I probably should explain to you the naming scheme for these videos, files that I'm going to be producing. So this one, for example, it's called W01L01b, and the W01 stands for the week. And this will be week 1 through 12. There's usually about 12 weeks in the class. And then each week there's going to be 2 lectures. So this L01 means the first lecture, which is scheduled for the Tuesday morning, lecture number. And then Thursday mornings will be 02. And if there's multiple parts, like this is the second part of the first lecture, it'll be either B, A, B, C, etc. Okay, so I'll try to probably not make these videos too long. Let's dig into some probability theory. In fact, actually, we're going to start with classical statistics. Okay, so or descriptive statistics, I guess we could call it. This is basically where probability theory started out. Several hundred years ago, was trying to describe large quantities of data in just a few concise numbers. So as I say here, the entire point of statistics is to attempt to describe an entire random phenomenon with just a few parameters. And I'm showing here an example that was very pertinent these days. The following plot shows us the number of COVID-19 cases by date of illness onset as of July 11th, 2020. And you can see there's a huge amount of information here. But associated with this information, then we can sort of try to make some basic statements about the nature of this random process. For example, we could say that somewhere in here there's some sort of measure of central tendency, which would be, say, about here. And we can call this X bar. And that's basically average. Sometimes also called sample mean. And another way of looking at this is that it is the balance point of that distribution. So if I cut that distribution out and balance it on my finger, that's where X bar would be. There's some other ways of measuring this, measuring the behavior or the nature of this information. There's another quantity which we call, it'll probably be about here, and we call this X tilde, and this is the median. And this is the point that divides the distribution in half. So there's 50% of the observations are above it, and 50% of the observations are below it. And I would guess that it's somewhere about where I've put it. So those are sort of 2 measures of central tendency. We can also talk about measures of dispersion or variability. And one of the common ones that we're going to talk about there is the so-called standard deviation, or sample standard deviation, which will be S. Sample standard deviation. And this is a measure of how wide this distribution is, how widely scattered the observations are. Well, this particular set of data, there's clearly a huge amount of information in the above plot, but of course what we're trying to do is say in just a few words the main characteristics of that information. And we can use this in the future to do things like compare how fast future diseases affect us. The average speed of this disease and its uncertainty would be quite valuable. These statistics would very much help us decide what the optimal risk-based approach to human survival might be. And so here's another plug. It's these sorts of issues that we're really grappling with these days. And so to really get ahead, we have to think about how to learn to characterize this sort of information so that we can use it in the future to protect ourselves from these sorts of diseases. Okay, so the basic background information that we need to know, we start by defining something called a random sample. And we'll use this quite a lot in this course, but this random sample is basically defined as a set of independent observations of a random process. And we're going to say that these sets of these observations, we're going to call them x1, x2, dot, 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 up to xn. And I'm going to write this as a vector. I'm showing a vector here as an x with a tilde underneath it. And that's a vector. And an x and a, let's say, a variable like c with two tildes underneath it is an array. Okay, so one tilde denotes a vector, two tildes denote an array. Let me just do that. Oops. Okay. So from these observations, we are interested in obtaining these basic summary measures of the population from which X bar was gathered. And we'll start with measures of central tendency. So I already mentioned this business of sample mean, but here now is an expression for the sample mean, and it is an equation that we've all seen many times, I'm sure. 1 over n times the sum of the observations is our average. So that's another way of putting this, is an average. We'll see later that when we talk about the mean, we're actually talking about the true population mean. And we would only know this if we sample the entire population. So as n goes to infinity, we get to know what the true mean is. And we're going to denote that with this variable mu sub x. Mu is the Greek letter for m, essentially. Okay, so let's illustrate this with an example. Suppose that our set of observations after ordering happens to be 1, 3, 5, 7, and 9. So I've got n equals 5 observations, and they are very nicely ordered from 1 to 9. And we can see, we know right away just by looking at this, that the average is going to be the midpoint, 5. In fact, we can get that. If x bar is now 1 over 5 times the sum of 1 plus 3 plus 5 plus 7 plus 9, which gives us 5. Now, what happens if our set of observations was changed a little bit? If I had the observations 1, 3, 5, 7, and 79, I would look at this and wonder to myself if this 79 isn't something called an outlier. And an outlier is basically a mistake. Did somebody write down 7, 9 instead of 9 when they were recording the information or the set of observations? So was that a mistake? It looks like it's a mistake because it's so far away from the rest of the observations. But you have to go back and check this, because if the set of observations actually did occasionally include these very, very large numbers, then you need to take that into account in your random model, because it's those sorts of extremes that often cause failures of systems. So if you ignore them, you're in trouble. So you basically have to go back and check your data and see if that 79 was actually a real observation or a mistake. In any case, now, if I recompute the average of those 5 numbers, I get a big change in the average. It jumps from 5 to 19. So I mentioned another possible measure of the central tendency, and that's the so-called sample median, and that's an x with a tilde on top of it. So a bar, straight line, is the sample mean. A tilde on top of it is the sample median, and its basic definition is it's the central value of an ordered sample, and its central value of n is odd, and an average of 2 central values of n is even. In the situation above, we had 5 observations, so it's the central value there is the middle one, which in this case is 5, and we'll see that in a minute. So the basic mathematical description is x over x of the n plus 1 over 2th index value of x. So if n is 5, we get 5 plus 1 is 6, divided by 2 is 3, so the median is x3, which is the 3rd element of the x array. If n is even, so for example, if I only had 1, 3, 5, 7, so I had 4, then the median is the average of the central two values. So it would be the average of 3 and 5. And the basic definition of the sample median is that value which divides the distribution in half. So 50% of the observations lie below it, and 50% of the observations lie above it. So here, I'll just repeat that example. If x is 1, 3, 5, 7, 9, my n is 5, which is odd, so my median is x3, which is equal to 5. So that's the fifth element. Oops, sorry. Where are we at here? The fifth element of this vector. And if we had our observations 1, 3, 5, 7, 79, 1, 3, 5, 7, and 79, we still have n as 5, so we're still looking at x3 as being our median, and so it remains unchanged. So the median is unaffected by this possible outlier, and so we say that the median is robust against possible errors. Of course, sooner or later, if you make too many errors, it's going to affect the median. But if we only had this one error here, it would make no difference to the median. And the median is probably, in this case, a better statement of what the central tendency of this data is. Okay, then the other thing that we can look at is how variable is our data. And there's a couple of ways we can look at that. One is just simply look at what is the range, our sample range. What is the distance between the minimum value and the maximum value? And the width of that different distance gives us a sense of the variability in our observations. So that can be computed as the minimum x value to the maximum x value. And if your set of observations are ordered from smallest to largest, that's x1 through xn. So if we use that same example where we've got x is equal to 1, 3, 5, 7, 9, then the range is, of course, 1 to 9. Another, I don't actually use the sample range that often because, again, it's very dependent on outliers. If I looked at the range, or the observations 1, 3, 5, 7, and 79, my range suddenly jumps to an enormous size from 1 to 79. Which isn't really that descriptive of this set of data. So a more usual or common measure of variability is the sample variance, which we're going to call S squared. And S squared will be an estimate of the true population variance, which we'll call sigma squared. And sigma is Greek letter S, basically. This S squared has a mathematical definition as basically the average of the squared deviations between the observations and x bar. We basically square this to get rid of the sign. If we'd left the square off, then the average of the deviations, just xi minus x bar, would always add up to be equal to 1. Because if x bar is in the middle, because the negatives and positives cancel one another. So to get rid of the negatives and positives, we square that. And we divide by n minus 1 instead of n to get so-called biased, unbiased estimator. And it's simply because the x bar is not known. It is actually more centered on the data than probably the true mean would be. So we divide by one less sample. So the picture of what's happening here is down at the bottom here. We basically have a set of observations, which I'm showing as blue circles, and our x bar is the green line through the middle, and then these deviations are the distances between the blue circles and the green bar, and we're looking at what is the average size of that squared deviation as our estimate of S squared. So on the right hand side I've shown another equation here, which is basically easier for hand calculations because we just add up the squares and then subtract n times the x bar squared, and then divide the whole thing by n minus 1. Okay, S squared itself has units of x squared. So if I say that the sample standard variance is 10, it doesn't really give you a good sense of what's going on. So it's more meaningful to take the square root of that thing and to find the sample standard deviation. S is equal to the square root of S squared. This has now the same units as x, and so is more meaningful. If I say that sample standard deviation s is equal to 3, then you know that most of our observations are between x bar plus or minus 3, plus or minus 3 in whatever units x is in. Another way of measuring variability is the so-called coefficient of variation, and this is very commonly used in engineering. It's just the ratio of the sample standard deviation and the sample mean. The advantage to this is that it gives us a relative measure of variability. So for example, if I told you the sample standard deviation was 3 and the mean was 1, then you've got a lot of variability. Basically, if you've got a mean here and sample standard deviation of 3, then most of your observations are between -2 and +4, which is quite a lot of variability relative to the size of the mean. On the other hand, if the mean is 1,000,000 and you've got plus or minus 3, you actually got very little random variability. In fact, I would probably not consider that to be random at all. So the first one would have a coefficient of variation of 3, s, 3 divided by 1, and the next one would be 3 divided by 1,000,000, very small coefficient of variation. Okay, just to give it a little example here, if x is, again, our set of observations 1, 3, 5, 7, and 9, then what is its sample standard deviation? We've already computed x bar. We know that it is equal to 5. So let's start by looking at the sample variance. We get s squared equals 1 over n minus 1, sum of the squared deviations, which gives me 1 over 4 times 1 minus 5 squared plus 3 minus 5 squared plus 5 minus 5 squared plus 7 minus 5 squared plus 9 minus 5 squared, and I add those all up, I get 10. So our sample standard deviation is the square root of 10, which is 3.2. So basically it's saying we got a mean of 5, and most of our observations are within about 3 of the 5, and this is true. We know that 3 of our observations are within 5 plus or minus 3. And our sample coefficient of variation is the ratio of s divided by x bar, which is 3.2 over 5, which is 0.6, showing reasonably high levels of variability. I mentioned that there's an easier way to compute this s squared value, and that's to use this other formula, s squared equals n minus 1, and then we just add up the squares and subtract n times the mean squared. So it's easier in general just to add up 1 squared plus 3 squared plus 5 squared plus 7 squared plus 9 squared, and then subtract 5 times 5 squared. And we get, of course, the same result, 10, but it's just a little bit easier to plug it all into your calculator. If I repeat all of this for the second set of data where we've got that 79 as our last observation, we knew in this case x bar was 19, and if I go through and do the same calculation for s squared, 1 over 4, and then I add up the squares of these observations and subtract 5 times 19 squared, I now get a huge jump in the variance, and that of course makes sense, sample variance. It jumps from 10 to 1130, and in fact the standard deviation now is about 10 times as big as it was for the other situation. This to some extent makes sense because we have this huge outlier that is telling us that there's a lot of variability, possible variability in this set of observations. Okay, so that's basically those are basically the two first and second order measures of the variability of a distribution. First order is the mean, and that's basically just adding up the x's. Second order is the variance, and that's adding up basically x's squared. So that's why we call it second order. There are higher order measures of distribution, one being skewness. So this measures the degree of symmetry of the distribution. If I go back up and look at that COVID-19 plot, we can see it's not exactly symmetric. It looks like it's got a longer tail out in the right-hand end as the number of cases diminish for this particular case for Canada. So that's a situation where the skewness would not be 0. It would be somewhat higher, denoting a high right skewed distribution. So if I show a set of, oops, sorry, where are we at here? If I show a set of observations, and I'm along this plot here, I'm now showing my observations red dots, and I've drawn through them my X bar. I see in the top one, I got just about the same number of dots above X bar as below X bar, so this I would say is a symmetric distribution. If I, on the other hand, see lots of dots close to X bar but below X bar, and a few that are farther away and above X bar, then I start to get this skewed distribution where the shape of the distribution looking in from the left into this distribution, I see a longer tail to the right, and so that's a higher skewed. And the actual measure that we do here involves cubes of the differences between my observations and X bar. We don't often use this this measure of skewness because there are basically, if we start cubing our observations, we're cubing also the errors that we're making in our observations. So the error in estimating the skewness is usually pretty high. So we don't usually bother with skewness and higher order measures of the shape of a distribution. Another way we can talk about these distributions and summarize them in a quicker way is to draw a histogram. And the basic idea is that we divide the range into a series of adjacent intervals or buckets and count the number of observations falling into each bucket and then plot it. So for example, suppose we have a set of 14 observations, and I've ordered them now from smallest to largest, starting from 0.7, 2.2, 2.5, 3.0, and so on and so forth, up to 8.3. Then, like I've said, we got 14 samples. Our sample range is 0.7 to 8.3. Well, we could divide that range, 0.7 to 8.3, into a series of buckets, but I think it's probably easier to actually assume a range that's a little bit outside the observed range, and so I'm going to assume a range from 0 to 9, and then make each of the buckets of width 1. So the first bucket would go from 0 to 1, second from 1 to 2, third from 2 to 3, and so on and so forth, up to 8 to 9. And then basically, if I look at my samples, I know that in the bucket 0 to 1, I've got one sample. That's the 0.7. In the buckets 1 to 2, I've got two samples, 2.2 and 2.5. Now, we're going to run into trouble when we talk about the bucket from 2 to 3 and 3 to 4, because there's a 3.0 in our observations, and so we have to decide, is it going to fall in the 2 to 3 bucket or in the 3 to 4 bucket? We can't put it in both buckets because then we're double counting. So we have to decide on a range for each bucket. So we could say the 2 to 3 bucket goes from 2 to 3 but includes 3. Or we could say it includes 2 but excludes 3. So the first one is this one. That includes the 3. And this one includes the 2 but excludes the 3. And then basically you would use the same rule for each of your buckets. So I think we're going to assume this one here, where we include the upper point and exclude the lower point. Okay, for the series of buckets xi to xi plus 1. And if we do that, then we get the following histogram on the left. Okay, yeah. So on the left we see that's what we get here. When we exclude the lower point but include the upper point. If, on the other hand, I did it the other way around, I include the lower point but exclude the upper point, then I get this distribution. And you can see it actually looks quite a bit different. And this decision about which point to exclude or include is entirely arbitrary. It's up to you. But I would just experiment and choose one that gives you the picture that you're happiest with. So basically, what I would Okay, yeah, okay. So what I would probably choose is the one on the right because it looks more like a common distribution, and we'll see that. Do I have it plotted here? Oh yes, I do plot it later. Okay. Okay, yeah. In fact, we're gonna later fit distributions to these histograms, and a common distribution is the log normal distribution, and it looks something like this. And so that looks like a reasonably good fit to that histogram that we see on the right. Now there's basically a problem here because if you look at that histogram and try and figure out what the area is underneath each of those, the sum of the areas under those blocks turns out to be equal to n delta x. So total area is the number of observations times the spacing. Okay, the spacing here is 1, and the number of observations was 14, so the total area here in this case is 14. Okay, and we can see that. The first block is 1 by 1, that's got area 1. The second block is 2 by 1, that's area 2. So basically I have the areas 1 plus 2 plus 4 plus 3 plus 1 plus 2 plus 1, which gives me 14. Also, if well, as we'll see later, the probability of an observation lying in some range is estimated from the above observations is the frequency divided by 14. So the frequency we just see in this plot, I should put the 4 in this one up here. So this one here is 4. So the probability of lying in the range 3 to 4 is going to be 4 of my observations were in that range, divided by the total number of observations, which is 14. Similarly for the number of observations between 0 and 9. But basically if we want to scale our histogram to give probability estimates, we only need to divide the vertical axis by that 14. So basically we got to end up with a new plot now. Oh, I should show the 14 here. And all we've done is change the vertical scale by dividing it by 14. So the plot looks exactly the same, it's just that we've squished it down, so now total area now is 1.0. Okay, so we get 1/14 plus 2/14 plus 4/14 and so on and so forth. Add them all up, you get a total area now is 1. And the reason we like to do that is because if we superimposed a fitted common probability distribution, and this will have, we'll see this later, have area under it of 1.0, then the two things are to the same scale, basically. So if I show my fitted log normal distribution here and superimposed on this so-called frequency density plot now, the scales are the same, so you can actually look at them and see if they compare reasonably well. And I should point out that when I fitted that distribution above, the actual distribution, oops, let's go back up here. The actual distribution is going to look like this. It's going to look like this because it has area 1. Okay, that's this thing here. So it's hard to compare these two measures of the set of observations. So that's why we scale the histogram to by dividing by n delta x. And then we can superimpose our fitted distribution and check to see what it looks like. And we prefer, at the end of the day, to use fitted distributions because they smooth out the irregularities that are coming from the sampling process itself and allow us to compute probabilities in a fairly simple manner. Okay, and that concludes our first lecture for this course. So I'll see you all in lecture number 2, which will be this coming Thursday. Thank you.